Welcome to Unit 1 of IT Complexity Analytics. I'm Roger Sessions. In Unit 1, I'm going to start by introducing myself, talk about a few legal issues you should be aware of, then we'll move on to the business imperative. What is it that the business cares about that IT Complexity Analytics can provide some value in? Then I'll talk about the complexity hypothesis, and that will lead us to an introduction to the general field of IT complexity. Of course, we'll be studying that in much more detail in the following 11 units, but this will serve as a general introduction to some of the important ideas. Then I'll give a bit of a review, as I'll always do, talk about the project that you're going to do, and then let you know about the quiz. Each one of these units has a quiz associated with it. They all have 10 questions, and that'll help you understand whether or not you are following the material. Let me start with a little bit about myself. I've been working in IT complexity analytics for at least 15 years now. I've taught the first accredited course, as far as I know, in complexity analytics at the graduate level at the University of the Andes. I've been a keynote speaker at many conferences, including 2 Gartner research boards. I've written a lot of books, white papers. Some of the white papers that I'm best known for are the IT complexity crisis, the mathematics of IT simplification, and a number of others. And I've also been recognized for my work in this field by being made a fellow by the International Association of Software Architects. 2 legal notes that I need to get out of the way. The first is that this presentation is copyright, so please don't redistribute this or invite your friends to view it if they're not so authorized. And the second is that the algorithms and methodologies discussed in all 12 of these units are patented and are intellectual property, and they are licensed independently from this presentation. This class has a total of 12 units. So in addition to this one, which is the introduction and overview, the next unit will go into complexity in a little bit more depth. In the third unit, I'll give you some mathematical introductions to this material. Some of you may not remember all of the math. It's not complicated math, but it's worth reviewing just so that you have it all in one place. In the fourth unit, I'll move on to measuring complexity. How can we actually look at 2 different systems and figure out which one is more complex and how much more complex is it? In the 5th unit, we'll move on to IT partitioning. Partitioning turns out to be the most important way of managing complexity. But there are a number of problems with it, as we'll see in Unit 5. And Unit 6 will help us to address some of those problems. We'll see how we can use equivalence relations to deal with some of the uncertainty that's inherent in IT partitioning. In Chapter 7, we'll talk about algorithmic driven partitioning and how it compares to decompositionally driven partitioning, which is the way we usually do things today. And in Unit 8, I'll move on to the snowman architecture, which is how do you actually apply this algorithmic driven partitioning into practice and drive it from the business down into the IT and data levels. In Unit 9, I'll move on to some guidelines about the architecture, a little bit more depth about things that you should be aware of, especially at the IT level. Unit 10, we'll talk about the SIP methodology in practice. SIP is the methodology that I refer to as the methodology that's used to create the snowman architecture and to do the algorithmic driven partitioning. So we'll talk about what that looks like in practice. In Unit 11, I'll talk about some of the challenges you can expect to run into as you implement some of these ideas and perhaps some of the ways you might address those challenges. And then the final unit, Unit 12, will be a review of all of the material. Each one of the 12 units has pretty much the same organization. In each case, I'll start with a review of pre-existing material. Of course, we won't need to do that for Unit 1 since we don't have any pre-existing material. And then the bulk of the unit will be dedicated to new material, and each unit will conclude with a project and a quiz. So the project is something that you'll be responsible for doing that will help to show you how these ideas can be applied in your real IT systems that you're developing, and then the quiz will always be designed to help you gauge how well you're understanding the material. Let's move into Unit 1, starting with the business imperative. Why does the business care about IT complexity? If you were to go to your business folks and ask them, what do you need from our IT systems that we're not delivering today? I think they would give you a list that would look something like the list on the left here. They would say, we need on-time delivery. You keep promising us systems to be delivered in 2 years, and then it takes you 3 years or 4 years, or sometimes you don't deliver them at all. We need you to deliver systems on budget. You can't tell us that a system is going to cost $10 million and then run over budget consistently to 15, 20, or even more. We need you to get these systems right the first time. This is really a problem. You deliver systems to us in which 20% of the functionality we need is missing, and another 20% of the functionality you deliver is totally inappropriate to what we've asked for. You need to make your systems more testable. They've got to be testable so that you have confidence that they're going to work and we have confidence that they're going to work. Your systems need to be more flexible. We're trying to respond to business conditions that are changing on a daily basis, and we need you to be able to change your systems just as quickly to support us. We can't have you telling us that every minor little change is going to take 6 months. Your systems have got to be more reliable. We cannot have systems that are going down every 2 months for days at a time. Our customers can't rely on them, and we can't rely on them. Security is a big issue. We're really worried about our customer data, and our customers are worried about that data. You've got to be able to absolutely assure us that the data that we're putting in these systems is absolutely secure. You know, we've heard a lot about cloud readiness, and we're really interested in being able to use the cloud in a cost-effective way. You've got to build systems that are able to do that. We've also heard a lot about agile development. We think it has a lot of potential. We think we could use small teams to deliver systems much faster. You've got to be able to design systems that are amenable to agile development. And we need accountability. We're getting clobbered by people coming in and needing to know exactly why data has changed. We're under regulatory requirements, and it's critical to us that when a customer record changes, we know who changed it, when it changed, and why it changed. If you're a typical IT person, you're probably feeling a little bit overwhelmed by this list. This is a lot of requirements, and they're all requirements that you haven't been doing a very good job of delivering up until now. So how are you going to change things so that you're starting to do a better job with these needs? The first thing you need to ask yourself is, are all of these needs related or are they independent? In other words, is each one of these line items here totally independent of the other line items, or are they all being driven by some common factor? That's important because if they're independent, then you need to attack each one of these line items independently, one by one. You need to figure out what can you do to make things on time? What can you do to make things on budget? What can you do to get things right the first time? But if they're related to each other, then you need to spend some time trying to understand what is that relationship and what is it that's driving each one of these items. If these attributes are all independent of each other, then we would expect them to rise and fall independently. In other words, sometimes the on-budget delivery might be made or it might not be made, and sometimes they might be on budget or off budget, but the knowledge that it was going to be delivered on time would not necessarily predict that it's also going to be delivered on budget, or getting it right the first time, or testable. In other words, none of these provides predictive value on how the others will behave. This is what we would expect if these attributes are all independent of each other. On the other hand, if these attributes are all related to each other, we would expect them to rise and fall together. So, for example, if we failed to deliver a system on time, we would also expect to deliver it off budget and not get it right the first time, and probably it wouldn't be testable or flexible or reliable. On the other hand, if we did achieve on-time delivery, we would also expect it to be on budget, right the first time, testable, flexible, and reliable. This is what we would expect if these attributes are all related to each other. In other words, if there's some common factor driving them all. If these attributes are all independent, then we're going to treat them independently. We're going to budget the improvement of each one of these independent of each other one. We're going to decide what is the priority of each one of these. We're going to assign specialists who understand how to make things testable, how to make things reliable, other specialists who know how to make them secure, and others who are specialized in cloud readiness, and project managers who know how to deliver things on time. So if they're independent, we need to attack each one of these attributes as a completely independent problem. That's what we mean by independent. On the other hand, if these attributes are all related to each other, then we need to address them very differently. Instead of attacking them one by one, we need to examine each one and see what is this common factor that's driving each one of these. What is the common factor X that's making things late, off budget, wrong the first time, not testable, inflexible, non-reliable, and insecure? What is this common factor X? And if we can identify that common factor X and put our money into addressing that factor, then we're going to address each one of these attributes that we care about. You can see that this question as to whether these attributes are related to each other or independent from each other is not just an academic question. It's a very important question because it tells us how we're going to deliver these attributes to the business. It turns out that when we observe these attributes in the real world, we notice that they behave in a very predictable manner. We have some systems that are very good, and good systems are good down all of the attributes. So if the system is delivered on time, it's probably going to be delivered on budget. We're likely to get it right the first time. It's going to be reliable, secure, etc., etc. So good systems are good throughout. Fair systems tend to start going down again as a group. If the system is delivered late, it's probably going to be delivered over budget. It's probably going to be hard to test, inflexible, etc., etc. And then we have systems that are very bad. They're very late. They're far over budget. They're never delivered right the first time. It's impossible to test them. So what we see is a pattern of consistency. This tells us that these attributes are all related to each other. They go up as a group and they go down as a group. We now have the answer to our question. Are these attributes related to each other or are they independent? Clearly, these attributes are all related. Since these attributes are related to each other, the next thing we need to figure out is what is the common driver? What is the common issue that's making these things go up or down? We need to know that because that's where we're going to put our money. A number of studies done in the 2005 to 2010 time frame seemed to indicate that the common factor X was the cost of the project, the overall cost of the project. It was observed by several studies that projects under $1 million had a greater than 75% chance of success. By the time the project size reached about $2 to $8 million, that success rate dropped to about 50%. And by the time the project size reached $10 million, the chances that the project would be successful dropped to under 10%, probably under 5% in most cases. This seemed to give clear evidence that the missing factor, the factor X that we're looking for, is the cost of the project. Further evidence that the cost of the project was driving all of these attributes was observed by noticing that these attributes tended to follow the project cost. So projects under $1 million, not only were they delivered on time and on budget, they were usually right the first time, they were testable, flexible, reliable, secure, and so on. Once the project reached that kind of in-between area, between $1 and $10 million, depending on the study, you could pretty much say that there was at least a 50% chance it would be late, over budget. It wouldn't be right the first time, it might be right the second or third time, it would be hard to test, pretty inflexible, not too reliable, security problems, and not as amenable to the cloud, not agile. Accountability was difficult to achieve. So we started to see this pattern. They all seem to be dropping at the same time, and then by the time the project reaches $10 million, all of these attributes go way down. It gets very late, far over budget, never right the first time, very insecure, etc. So this, again, seemed to give evidence that the common factor is just the cost of the project. When the cost goes up, the attributes go down. When the cost goes down, the attributes go up. That seems to be what was being shown by this data. This leads directly to the project cost hypothesis, the hypothesis that the project cost is the common driver of all of these attributes. But there are problems with this hypothesis. If cost was the common driver, we would expect the rate of deterioration across these attributes to be consistent across organizations. And in fact, we don't see that. In fact, we don't even see a consistent rate of deterioration within an organization. Some organizations, and sometimes within that organization, we see rapid deterioration as the cost goes up. Sometimes we don't. Sometimes we see organizations that experience very little deterioration, and sometimes projects within an organization buck the trends that we see elsewhere in that organization. So this is not predicted and not consistent with the cost hypothesis. The obvious conclusion from this is that cost is an indirect factor. What that means is that cost is having an impact on these attributes, but it's doing so indirectly. There's actually some other factor, X, that cost is affecting. And this indirect factor, X, it's what's driving the rest of these attributes. So as the cost increases, the X increases, and that brings down the attributes. And as the cost increases more, that tends to increase X even more, and that drives the attributes even further down. So we do believe that there is some relationship to cost, but it's an indirect relationship. Cost is driving some X, and we still, if we can find that X and understand the relationship between cost and X, then we have some chance of solving our problem. So where are we now? We can say with some confidence that cost drives some factor X, which is yet to be identified. This factor X makes it harder to build good systems. In other words, to deliver all of the attributes the business is looking for. But there is some good news here, because we see that the deterioration of X with cost is not constant. That tells us that some organizations, or at least some groups within the organization, are better at managing X than others. And that is also good news because it tells us that X, whatever X is manageable. We are left with two important questions. What is X? And how can we better manage X? This brings us directly to the next topic, the complexity hypothesis. The complexity hypothesis, namely that complexity is this missing factor X that is being driven by cost and in turn driving all of these attributes, is supported by the fact that we can show that complexity increases with project cost. We can show that mathematically, and we can also show mathematically that the relationship between complexity and project cost is something that can be adjusted depending on how we're approaching the project. That would explain why we sometimes see organizations have a lower or higher rate of deterioration of their attributes with the cost of the project. That's explained by the fact that it's not cost that's driving these attributes, it's complexity, and the relationship between cost and complexity is to at least some extent manageable. The implication of this is that if we want to address all of these attributes that the business cares about, we need to do it by attacking the real enemy, and complexity is the enemy. Let's return to an observation that we made earlier, namely that these attributes that the business cares about behave as related groups. They go down together and they go up together. Since we know that they're related groups, that tells us something about how we should approach them. But how are we approaching them today? And is the approach that we're using today likely to be successful? Remember that we've identified the driving problem as complexity. And we've said that if they're related groups, which we have shown that they are, then we should be attacking the common problem, that is, the complexity that's driving each of these issues. If, on the other hand, we were approaching them as independent problems, then we should not be attacking the complexity. Instead, we should be attacking each one of these line items on a case-by-case basis. So let's see what we're doing today. Are we attacking complexity, or are we attacking the line items on a case-by-case basis? It's pretty clear today that we're attacking these on a line item basis. So for example, if we look at on-time delivery, we assume that the problem there is that we're not doing enough project management. And as the project gets bigger, we know we're going to be even more challenged to deliver the project on time, so we put even more project management in place. And as it gets into the $10 million range, we throw even more project managers on it. Similar for budget. We put a certain amount of effort into tracking a $1 million project, more effort into tracking the project once it exceeds $1 million. And as the project gets larger and larger, we put more and more money into tracking the budget. And the same thing goes for each one of these line items. So it's very clear that whereas we should be attacking the common problem that's driving each one of these line items, which is of course complexity, instead we're attacking these line item at a time. And there's no possible way that can be successful. There are three areas we can try to attack to solve the problem of delivering these attributes that the business cares about. We could be trying to do something about the cost of the project. We could be trying to do something about the complexity of the project. Or we could try to do something on a line item by line item basis, which we've already shown is not going to work. So that leaves us cost and complexity. The cost is not something we're going to be able to do a lot about because a large project is going to be expensive. What we can do something about is the relationship between cost and complexity, because we've already shown that some companies do a good job at managing the complexity and others don't. What's left for us to understand is what is the difference between those two approaches so that we can choose an approach on complexity that's going to be successful. And that, of course, is the topic of this entire class. The problem as to why IT is failing the business can be summed up in this slide. We think cost is driving the problem. It isn't. We're totally ignoring what is driving the problem, which is complexity, and we shouldn't. And we think we can solve the problem by focusing on the attributes, which we can't. If we're going to solve the real problem, which is complexity, we should start, of course, by understanding something about complexity. So let's take our first introduction to the topic of IT complexity. A good place to start in understanding complexity is to define what we mean by complexity. So I define complexity as that attribute of a system that makes the system difficult to understand. And of course, if the system is difficult to understand, it's difficult to maintain, it's difficult to modify, it's difficult to make secure. So complexity is what makes a system difficult to understand. There are two basic forms of IT complexity. There's what we call functional complexity and what we call dependency complexity. Let's take a look at each of these. Functional complexity is the complexity that comes from the amount of functionality in a system. So as we add more and more functionality to a system, we add more and more complexity to that system. In this slide, the blue dots indicate functions, and we have 4 systems, and as we go through time, we're adding more and more functionality to each one of these systems, and thereby increasing the complexity of each of these systems. So think of this as like the complexity that increases as we go from a wheelbarrow to a car, which has more functionality than a wheelbarrow, and going then from a car to an airplane, which of course has more functionality than the car does. That's functional complexity. Dependency complexity, on the other hand, is the complexity that we get from interdependencies between systems. So here we're showing 4 systems, and their functionality, represented by the blue dots, is not increasing. But the number of interdependencies, represented by the lines between the systems, is increasing. This is the kind of complexity increase that we see as we go from a backyard runway that can only support one single plane to a multi-plane runway that's supporting a small airport to Chicago O'Hare, which is supporting a huge number of planes coming in every day. That represents the complexity increases that we see as dependencies between systems increase. Now that we've looked at complexity, let's look at the other side of the coin, simplicity. Simplicity is simply defined as the lack of complexity. So there's really no such thing as simplicity. You can't add simplicity into a system any more than you can add cold into a system. If you want to add cold into a system, you have to do it by removing heat. And if you want to add simplicity to a system, you have to do it by removing complexity. So simplicity is just the lack of complexity. If one system is less complex than another, then the first system is more simple than the other. As I said earlier, there are 2 ways to add complexity to a system. You can either do it by adding functionality to a system or adding interdependencies to that system. It stands to reason, therefore, that there are 2 ways to increase the simplicity of the system. You can remove functionality from the system, or you can decrease the dependencies from that system to other systems. Since adding functionality and adding dependencies increases complexity, removing them decreases complexity and thus increases simplicity. Let's take a brief look at how we go about measuring complexity. Complexity is measured in SCUs, or standard complexity units. A standard complexity unit is defined, a single standard complexity unit is defined as the amount of complexity in a system with one business function and no dependencies. Now, we don't see systems like that very often, but that is our standard measure, so we use that as the way to measure the amount of complexity in a system. It doesn't mean that a system with 100 business functions is going to have 100 standard complexity units, because as we'll see, the relationship between SCUs and functionality is an exponential function. But it's a way of standardizing across different types of systems and different types of complexity. Both functional complexity and dependency complexity are both measured in SCUs, and SCUs are a way to standardize across these two very different types of complexity. So one SCU is the same amount of complexity, whether that SCU is coming from functional complexity or dependency complexity. Now, we never see systems with 1, 2, or even 10 SCUs. Typically, we see systems that are in the many thousands of SCUs. So a better way to look at this is that two systems, each with 10,000 standard complexity units, each have the same complexity, even if one of those systems is coming primarily from functional complexity and the other one is coming primarily from dependency complexity. Another point I'll make about SCUs is that it's a linear measure. So if you have one system that has 10,000 SCUs and another system that has 20,000 SCUs, the system with 20,000 SCUs is twice as complex as the system with 10,000 SCUs. Now, don't confuse the exponential relationship between the number of functions and the number of SCUs with the relationship between SCUs themselves. So although the relationship between functionality or dependencies for that matter and SCUs is exponential, in other words, the SCUs go up much faster than the number of functions or the number of dependencies goes up, the SCUs themselves are linear. We'll talk much more about this later, so don't worry too much about it now. I just want to give you an introduction to some of the things that we use when we're trying to measure complexity in systems. Let's also look at simplification. Simplification is the word that I'll often use to apply to what we do to an IT system. Or we might say we're going to simplify the IT system, or we're going to apply the process of simplification to an IT system. Either one of those means the same thing. It's essentially the process of reducing the SCUs in an IT system without reducing necessary functionality. Let's look at the simplification process in practice. Here we have a very simple IT system. It only has 8 functions and they're all contained within a single system. So the total complexity in this system is coming only from functional complexity, not dependency complexity. The reason that it's not coming from dependency complexity is that there's no dependencies between this system and something outside of itself. So while there are dependencies between the functions, those functions are all contained within a single system. So the only complexity we have in this system is functional complexity. Now, how might we go about simplifying this already very simple system? The first thing that we might try to do to simplify this system is to remove functionality from it. So, for example, if we could remove half of the functionality from the system, we would have a dramatic impact on the complexity of the system. We would reduce it from a starting point of 512 SCUs to down to 64 SCUs. That would be almost a 90% reduction in complexity. Now, earlier I said that simplification is the process of removing complexity without removing necessary functionality. So you might think that this is flying in the face of that. However, my assumption here is that we had 4 functions that were really not necessary from the business perspective. If the business doesn't really care about this functionality, then IT putting them in is simply increasing the complexity without increasing the deliverable functionality to the business, because the business doesn't care about that. So if you can find functionality that can be removed without impacting the business requirements at all, then that's certainly an easy no-brainer starting point to reducing the complexity of the system. Now, assuming that you've done a good job of your requirements analysis, and we'll have a lot more to say on that later on, the chances are you don't have functionality in there that the business doesn't care about, because you would have understood that by putting in functionality that the business doesn't care about, you're dramatically increasing the complexity of the system without increasing the business value of that system. So assuming that we don't have a lot of functions lying around that we can get rid of, what else can we do to simplify our system? Usually, the process of simplification is going to entail partitioning the functionality that we have there. So it's a matter of splitting the large system into smaller systems in such a way that the overall complexity is decreased. So here, by carefully choosing 4 functions that we're going to put in one subsystem and 4 in another, we've had a decrease in the total complexity of the system from 512 SCUs down to 131 SCUs. Most of the SCUs in the partition system are coming from functional complexity, but you can see that we now have a little bit of dependency complexity due to the interdependency between function F and function C. But overall, even though we've increased the dependency functionality, we've been able to dramatically decrease the functional complexity. So the net result of this is a great reduction in complexity from 512 to 131 standard complexity units. So partitioning functionality is a great way of reducing functional complexity. The problem is that functional complexity isn't the only thing that's contributing complexity to the system. As I talked about earlier, complexity has 2 faces. It has functional complexity and it has dependency complexity. What we typically run into is that as we reduce the functional complexity by partitioning, we increase the dependency complexity by partitioning. In fact, you can almost guarantee that you're going to increase the dependency complexity when you partition functionality. The real question becomes, can you decrease the functional complexity by more than you increase the dependency complexity? So on balance, can you come out ahead? So in that partitioning that we did before that resulted in 131 SCUs, on balance we came out ahead. We increased the dependency complexity, but we decreased the functional complexity so much that that was a small price to pay. In this partitioning exercise, the third one shown on this slide, we have a lot more dependency complexity. We have exactly the same amount of functional complexity, but now the increase in dependency complexity has completely swamped the decrease in functional complexity. So we have a net increase in complexity from where we started with 512 SCUs in the unpartitioned system to 814 SCUs in this newly partitioned system. So we've actually made this situation much worse from a complexity perspective by doing the partitioning. We've seen that a good partition can greatly reduce the number of standard complexity units in a system, and we've also seen that a bad partition can greatly increase the number of standard complexity units in a system, usually by increasing the dependency complexity more than we reduce the functional complexity. So how do we know we've found the best possible balance between these two aspects of complexity, functional and dependency complexity? It's not easy, and the problem is greatly exacerbated simply by the large number of possible ways there are of partitioning a system. So if you take a system that we have here with 8 functions and a total complexity of 512 standard complexity units, there are millions of ways that this system could be partitioned. This is just a small collection of the number of possible ways, and you can see even here the total complexity that we have ranges from a low of 131 standard complexity units to a high of 838 standard complexity units. That's a big range. And as we'll see later, since complexity drives cost, that means that probably the 838 standard complexity unit system is going to cost Well, whatever the difference is between these two, probably 5 times as much as the 131 SCU system would cost to build. So the implications of the increase in standard complexity units can be really important when we're looking at issues like price and security and reliability, all of which, as we'll see, are driven by standard complexity units. So in this huge number of possible partitions, how do we find the best possible one? How do we be sure that we're avoiding the worst possible ones and even some of the ones that aren't as good as the best possible ones? So if we have millions of ways of partitioning, how do we hone in? How do we zero in on the one or maybe a small number of partitions which are going to give us the best possible complexity rating? In other words, the lowest possible SCUs to deliver a certain amount of functionality. As we have seen, partitioning can be a very effective strategy to reducing complexity. Here, for example, we have a system whose complexity has been reduced from 512 to 131 SCUs simply through partitioning the functions correctly. Now, partitioning is being widely used today. We see it used in business process modeling, and capability modeling, and service-oriented design. So people are using partitioning in many different aspects of IT design and implementation. The question then is, why are we having so many problems? Why is complexity still such an issue for these large systems if we're using partitioning in so many different areas? Although we are doing partitioning today, it turns out that we're not doing it correctly. We're using a process that I call decompositional design. Decompositional design looks like this. We start out with a very large, undifferentiated system. We decompose it into smaller pieces. We decompose those smaller pieces into yet smaller pieces. And we continue this process until we reach some collection of small pieces that we think is the appropriate amount of decomposition. Decomposition seems like a good idea until you take into account what it usually does to complexity. So let's consider complexity in the decompositional equation. Here we have a large, undifferentiated system that starts out with a complexity of 64,000 SCUs. When we finish our first decomposition, we end up with two smaller pieces. Each one of those smaller pieces has many fewer functions than we started out in the large, undecomposed piece. So we've certainly done a good job of decreasing the functional complexity, but look what we've done to the dependencies. We've introduced all kinds of dependencies. The net result is that we actually haven't decreased the complexity at all, and in fact we've increased it from 68,000 to over 71,000. How have we done that? We've done that by adding more dependency complexity than we've decreased by reducing the functional complexity. And this is typically what we see with decompositional design. Maybe you think that I'm not being fair to decompositional design. We've only done the first decomposition after all. So let's see what happens when we break those two pieces into four pieces. In other words, the second part of the decomposition. What we have now is we have four pieces, and from a functional perspective they look quite good. They're getting small, they seem to be manageable from the number of functions in each one, and we can assume that the functional complexity has decreased dramatically. But look what's happened to the dependency complexity. That has gone way up. And on balance, we've gone from a system that started with 68,000 SCUs, and we're now over 100,000 SCUs. In other words, we've almost doubled the complexity of the system by doing what we thought was the right way to make it simpler, which is to do decompositional design. So there's obviously some problem with decompositional design. In fact, there are three problems with decompositional design. The first is that it's non-directed. Non-directed means that there are many possible outcomes from doing a decompositional design. And in fact, mathematically, we can show that any one of the possible partitioning outcomes can be arrived at through decompositional design. And we already know that many of the partitioning solutions are poor solutions from a complexity perspective. The second problem with decompositional design is that it's completely based on gut feel. So that means that there's no reproducible methodology for driving the decompositional design. It's really based on what one person thinks is the best way to decompose it versus the way another person thinks is the best way to decompose it. What this means is that in practice, we will often see multiple architects doing a decompositional design on the same basic system come up with totally different decompositions. Of course, each one of those is going to have some specific complexity rating associated with it, and some of them are going to be low and some of them are going to be very high. Some of those architects may have stumbled on the lowest possible complexity partition, but most of them probably didn't. The third issue is that it completely ignores the complexity problem. So it has no way of taking into account complexity because partitioning is usually done before we even know what the dependencies are. So even if the partitioning wanted to take into account the complexity, it doesn't have the data it needs to do so. Well, if we aren't going to use decompositional design to drive our partitions, what are we going to use? What we're going to use instead, and what we're going to learn about in this class, is algorithmically driven partitions. Algorithmically driven partitions are much different than decompositionally driven partitions. Whereas decompositionally driven partitions are non-directed, gut feel based, and completely ignore the complexity issue, algorithmically driven partitions differ in all three of these areas. First, they're directed, which means that instead of any number of outcomes being a possible result from applying the partitioning algorithms, are very directed. There's only one possible outcome when you're using an algorithmically driven partition. They're mathematically driven rather than gut feel based. So instead of it being dependent on the particular person who's driving the design, it's driven by the mathematics that determines what that design should look like rather than what you think it should look like. And third of all, instead of ignoring the complexity issue, the algorithmically driven partitions attack complexity head-on. The algorithmic process that we're going to use for driving our partitioning is one called SIP, which stands for Simple Iterative Partitions. We'll talk a lot more about SIP during the rest of this class, but I just want to give you an introduction to it here. SIP starts not by doing a decomposition, but identifying the business functions that will eventually live in the different subsets. The next thing that happens is we use the SIP algorithms to identify which functions should live together in the first subset. Once those functions are identified, they are placed together. Then we apply the same algorithm to the remaining functions, identifying which is the next group of functions that should live together in the same subset. We then continue this process, identifying new functions and moving them to new subsets. We continue this process until we get to the last group of functions that need to live together, and like the others, they become their own subset. Once we have the last subset identified, we create that last subset. And now we have a fully partitioned system, and we haven't done any decomposition at all. And because the algorithms that we've been using are directed, there's only one possible outcome for this partitioning process. Having completed the partitioning process, we can add in the dependencies and calculate the SCUs. If we compare the result of doing a decompositional design as opposed to an algorithmically driven design, especially using the SIP algorithms, we see a huge difference in the resulting complexity. Here we've done a full decomposition into 7 subsystems, and you can see that the decompositionally designed system has a total complexity of almost 42,000 SCUs, whereas exactly those same functions partitioned algorithmically have well under 2,000 SCUs. So there's a huge difference in the complexity of these two systems. The complexity will drive all the other factors that we care about. So not only will the decompositionally designed system have a poorly optimized capability map or service-oriented architecture, if that's what we're doing, it's also going to be a system that's not going to be easy to use agile because there's too many dependencies and too much complexity. It's going to be hard to secure because there are too many points that the system can be attacked. And all of the other attributes that we talked about earlier are going to be in much worse shape. The algorithmically designed partition is going to be very optimized. If it's a capability map, it'll be a highly optimized capability map. If it's a service-oriented architecture, it'll be a highly optimized service-oriented architecture. It's going to be easy to apply agile development on this because the dependencies are very minimal. Easy to secure, high reliability, and again, all the other business attributes that we started this unit talking about are going to be much more optimized than they will with a decompositional design approach. So you can see the benefits of using an algorithmic approach rather than a decompositionally designed approach. We've covered a lot of material in this unit. Let's do a review. I started this unit by talking about some of the business concerns. These are areas that the business cares a lot about that IT isn't doing a very good job at today. So for example, the business needs us to deliver things when we say we're going to deliver them. We don't do that for large systems. The business needs us to give accurate predictions of what the systems are going to cost. Typically, these large systems go way over budget. The business needs better business IT alignment, which means that when we deliver functionality, that functionality needs to be the functionality that the business really needs. The business needs our systems to be secure, maintainable, and reliable. They need to have good performance, and they need to meet the agility that the business needs in order to rapidly respond to changing business conditions. And of course, everybody's worried about how best to use the highly efficient platform we know as the cloud. All of these issues that the business cares about are very important, of course. We need to resolve how we're going to be able to deliver things on time, on budget. We need to figure out how to do a better job of securing our systems. We need to figure out how to use the cloud more efficiently. But our inability to resolve these issues is really a symptom of the underlying disease. And if we don't cure the disease, there's no point in attacking the symptoms. That's not going to solve anything. The disease that we need to attack and cure is complexity. In IT systems, complexity comes in two forms. The first form is functional complexity. This is the complexity that increases as we add more and more functions to our systems. The second form is dependency complexity. This is the complexity that increases as we add more and more dependencies between our systems. If we're going to try to eliminate complexity, we need to be able to measure it because we can't eliminate what we can't measure. Or at least we can't tell how successful we have been at eliminating it. So the measure that we use for complexity is standard complexity units, abbreviated SCUs. One SCU is the amount of complexity in a system with one business function and no dependencies. SCUs are important because they allow us to compare the complexity of different systems, and they also allow us to standardize the two different types of complexity. Many people talk about simplicity or simplification instead of complexity, but we understand that these two concepts are closely related. Simplicity is really the absence of complexity. This is the same as cold, which is the absence of heat. So if we want to make things simpler, we need to remove complexity. In other words, if we decrease the SCUs in a system, the standard complexity units in a system, we're going to make it less complex or we're going to make it simpler. They're both saying the same thing. Now that we can talk in a meaningful way about complexity, we can also talk about what we mean by the best possible IT system. The best possible IT system is the simplest system that does everything the business needs it to do and has the lowest amount of complexity. In other words, the best system is the simplest system that meets the business needs. We've reached the end of Unit 1. Don't go away because I'm going to talk about your project in a moment. But let me leave you with this quote by Steve Jobs. "Simple is harder than complex, but it is worth it. Once you achieve it, you can move mountains." I hope by the end of this class you're going to be moving some mountains in your organization. This is the project that I'd like you to complete before we reconvene. Imagine your CIO is giving a speech to your organization. She says, "Our IT systems need to be more blank, 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 and blank." Think of 4 words or word combinations that are likely to replace these blanks in your CIO's speech. Once you've done that, consider a design for an IT system that is about to be implemented. How does complexity impact your ability to deliver what the CIO has asked for? Which complexity impacts you the most, functional complexity or dependency complexity? Write this down and we'll reconvene soon. I'm looking forward to seeing you again. Bye for now. And don't forget to take your quiz.